So in this class we are discussing problem solving using Gauss's theorem, and in the process we learn a few new things about the mathematics of Gauss's theorem, which is very interesting. To start with, a very elementary problem. Consider a square sheet. Now we have here a square sheet having an edge length A. Now at a distance A by 2 above the center of this square sheet, we have a point charge Q. So this is the center point here. At a distance A by 2 above this square sheet, a point charge Q is placed here. Let's say it is positive. This is a perpendicular distance A by 2 above the center of the square sheet. The square sheet has the square surface here has a side A, and we have been asked to calculate the electric flux through this square surface. Now to calculate the flux through the square surface, if we were to calculate the electric field due to the charge at various locations, then the field at various locations on this surface will have different magnitudes. Also, the field will not be normal to the area, it will have different magnitudes, different directions everywhere, and therefore the calculation of flux on the square surface by using the definition of flux will be a very difficult task here. So we have to come up with an ingenious solution for this problem, and to do that what we will be doing is we will be placing such square sheets on top of these sides vertically like this. So we have another such square sheet of side A, and we've kept it vertically on this side. We bring another such square sheet and place it here, then another one and place it vertically over here, and another one on this side, and we have one more such square sheet which we place right on top. Now this produces a cube. Now we have a cube over here. This cube has a side A, and charge Q has been kept at the center of this cube. We have been asked to calculate the electric flux through the face ABCD of this cube. Now if you look very carefully, the way this cube has been constructed, the charged particle is exactly at the center of the cube, at the geometric center of the cube. And since the charge is at the geometric center of the cube, the flux through each face of the cube is same, right? Flux through each face of the cube is same. Let's say that flux is phi. So phi is the flux through any one face of this cube, and the flux through all the other faces therefore is also phi. Now we have constructed a complete cube out of these 6 different sheets of square shape, and the charge Q is at the geometric center inside this closed surface. Now if we treat this cube as a Gaussian surface, then the total flux through this cube total flux through the entire cube will have to be equal to the enclosed charge Q divided by epsilon naught. Now the total flux through the cube is the sum of the flux or fluxes through the individual surfaces. Now the flux through any one of these surfaces, flux through any one of these faces is phi. And therefore the total flux through the entire cube will be 6 times phi, and this will be equal to Q by epsilon naught. Phi therefore comes out to be Q divided by 6 epsilon naught, and that's the flux through any one face, and ABCD being one of those faces, this is also the flux through the face ABCD of this cube. So a very elementary problem to just warm us up with. Next we take up a slightly more complicated problem where we'll be placing the charge at a somewhat different location. Now that next problem, what we'll be doing is we'll be placing the charge Q at one of the corners, and then we'll calculate the flux through the faces of the cube. What we are doing is, we have the same old cube that we constructed in the previous problem, but this time the charge Q is placed on one of the corners of the cube. And now we are interested in calculating the flux through the individual surfaces. Also we are interested in calculating the total flux through the entire cube. Now the charge has been kept at the corner F of this cube, and the magnitude of the charge is Q. It's a point charge, and we have a cube here, so all the sides are identical ones. I have named these vertices of the cube as A, B, C, D and E, F, G, H. Now the cube here has two kinds of surfaces. First category of surfaces are the surfaces which are in contact with charge Q. The first category of surfaces are the ones that are in contact with the charge Q, and that means we're talking about surfaces F, B, C, G. F, B, C, G. This surface is in contact with Q. F, E, H, G is in contact with Q, and A, B, F, E is also in contact with charge Q. Then there are three other surfaces, A, B, C, D, C, D, H, G and A, D, H, E. A, B, C, D, D, C, G, H and A, D, H, E. These three are not in contact with charge Q. So there will be one value of flux for the surfaces which are not in contact, and there will be another value of flux for surfaces which are in contact. Now it's quite easy to anticipate the flux through the surfaces which are in contact with charge Q. For example, if you look at EFGH, the field due to charge Q on the surface EFGH will be always tangential to the surface. For example, if we have this board and we keep a charge Q at this edge, this corner of the board, then at any point on the board the field will be tangential to the surface of the board. So for EFGH, because the field is tangential to the surface at all locations on EFGH, the flux is 0. Similarly, the flux on FBCG is 0, and the flux on EFBA is also 0. The flux on ABCD, DCGH and EADH, on these three the flux will be identical, but it will be definitely non-zero. So flux through surface A, B, F, E is 0. Flux through surface F, B, G, F, B, C, G is 0. And the flux through EFGH is also 0. The charge is in contact with these three, and the field at any point on these three faces, the field will be always tangential to these surfaces, and therefore the flux comes out to be 0. Now flux through the other three, that is A, B, C, D, is equal to the flux through C, D, H, G, and this is also equal to the flux through EADH. So these three are equal fluxes. We need to calculate the magnitude of one of them, or maybe even the sum of all the three of them. This is what we'll be doing. The flux through each one of these faces we are now going to calculate. Now to do this, we have to do a bit of jugglery. This here is the cube that we originally had. The charge Q is at the rear side corner F, and what we do now is we construct another cube to the right of this given cube. So we have this cube over here, and we construct another cube to its right, another identical cube here. So then we have two cubes, and below those two cubes we construct another two identical cubes like this. So we now have a set of 4 cubes here. The job is not done yet. What we will also need to do now is construct 4 such identical cubes behind these cubes. So we are constructing 4 more cubes right behind these cubes. And by constructing those 4 more cubes, we end up having a large cube which is made up of 8 such smaller cubes. So we have 8 such cubes now, and they form a larger cube, and charge Q is now placed at the center of that larger cube. I hope that is clear to you. So what we did first was we had this cube A, B, C, D, E, F, G, H. To its right we constructed another identical cube. Below those 2 cubes we constructed 2 more cubes, and then we had 4 cubes, and then we had 4 more cubes right behind these cubes, constructing a larger cube made up of 8 such cubes. The charge Q that we had at corner F is now at the geometric center of the larger cube, and for the larger cube, let's say these are points, D, F, D, we can't have F, K, D, K, L, M. Okay. Now let's have a look at the surface D, K, L, M. The flux through D, K, L, M will be Q by epsilon naught. Q by 6 epsilon naught. This is something we've already discussed in the previous problem, that if you have a cube and a charge Q at the center of that cube, then the flux through any one of the faces equals Q by 6 epsilon naught. So that's the flux through this large face here. But we were interested in the flux through A, B, C, D. Now since the charge Q is at the center of the cube, the flux through these 4 surfaces, this surface A, B, C, D, then you have this surface here, B, we can K, L, M, N, we can call this point O. So you have this surface A, B, C, D, and you have B, N, K, C, then you have O, L, N, B, then you have A, M, O, B. So we've divided this large face into 4 equal parts, and since the charge is symmetrically located with respect to all of them, the flux through each one of these individual faces will be equal. So if you have these four surfaces, the flux through each of these four surfaces is equal, and the flux through the entire large surface is given, then the flux through any of those four surfaces, let's say for example A, B, C, D, will be 1/4 of the flux through the entire surface. So 1/4 of this comes out to be Q by 24 epsilon naught. So that's the slightly more interesting version of that previous problem that we discussed. The flux through any one of these faces, for instance A, B, C, D, is so much. Since the flux through each one of these surfaces is same, the total flux through the entire cube will be the sum of these fluxes. So 3 times of this and 3 times of this will be Q by 8 epsilon naught. So that's a nice simple problem. Now we'll take up some slightly shall we say more interesting problems. The next problem we are discussing will be taking up a variable charge distribution, and we'll then try and examine the electric field, or rather the flux and relation between flux and the charge density at a specific sort of location. Now consider a region of space where the electric field is given by E naught times x, x is the x coordinate, into I cap. And the y and the z components of the field are 0. And in this region of space here, we have a cube placed. So we are placing a cube here, and this cube has an edge length A. This is the x-axis, y-axis, z or z-axis, and this is the electric field in this entire region. We have been asked to calculate the charge enclosed inside the cube. Now it's a fairly simple problem from the look of it. We have this cube and we have an electric field in this region of space, and we've been asked to calculate the total charge that's enclosed inside this cube here. The solution looks kind of obvious, that let's calculate the total flux through the cube. We already know the expression for the electric field, so we'll calculate the flux through the cube, and that total flux will be equal to obviously the enclosed charge inside the cube divided by epsilon naught. So looks like a simple process, and it should be simple. Let's make calculations. Let's name these surfaces of the cube. So for that we'll be naming the vertices A, B, C, D, and we have E, F, G, H. So we have this cube, and these are the corners of the cube that I have named A, B, C, D, E, F, G, H, and this is the electric field here. Now the direction of this electric field is the x-axis direction. So what we'll be doing now is we'll be calculating the flux of this field through each of these individual faces of the cube. let's start with the EFGH. Now the field is in x direction, so as far as the surface EFGH is concerned, this is the electric field in positive x direction. Now I hope you can visualize here that this electric field is tangential to the face EFGH. We're talking about the face EFGH. This electric field is tangential to EFGH. EFGH is actually the xy plane and the field is in x direction. So this field is tangential to this face and therefore the flux through this EFGH is 0. Let's now move on to the next phase, and the next phase is ABFE, right? The next phase we are looking at is ABFE. Looking at ABFE, the electric field is again along x-axis direction, and you will again notice that the electric field is tangential to ABFE. Since the electric field is again tangential to ABFE, the flux through ABFE is also 0. Now there will be a lot of phases here where we'll have 0 flux. Next we'll consider ABCD. ABCD. Now as far as ABCD is concerned, again the electric field will be tangential to the surface. Being in positive x direction, the electric field on ABCD will also be tangential, and therefore the flux through ABCD is also 0. Okay, so flux through EFGH is 0, flux through ABFE is 0, flux through ABCD is 0. Let's now calculate the flux through BCGH. BCGH. BCGH is this top surface here. Again, if you look at the electric field on BCGH, it will also be tangential to this surface. And so the flux through it is 0 as well. So flux through BCGH is 0 again. So far so good. We have 4 of these faces: A, B, CD, BCGH, EFGH and ABFE. The flux through all 4 of them is 0 because the electric field is tangential to these surfaces. Job easily done. We get 0 flux. Let's now look at AEHD. Now AEHD is in the YZ plane. AEHD is in the YZ plane, and in the YZ plane x coordinate is 0 at all the points, and if x coordinate is 0 at all the points, the electric field is 0. So on this surface electric field is 0 throughout, and if electric field is 0, the flux through AEHD will also be 0. So we have calculated flux through 1, 2, 3, 4, 5 surfaces, 5 faces of the cube, and for all those 5 faces the flux is 0, which leaves us with only one face of the cube where we need to now calculate flux, and that face is BFGC. BFGC. Now for BFGC, the electric field is normal to the surface, and on BFGC the x coordinate at all the points will be equal to a. Since x coordinate is equal to a for all points on BFGC, for instance, at F the x coordinate is a. All points on this line therefore are at same distance a from the YZ plane, and therefore the x coordinate all over this entire face will be a, and therefore the field has a magnitude E naught times a. So E naught a is the electric field. It is constant at all the points, and it is also perpendicular to the surface, normal to the surface at all these points, and therefore the flux will be the magnitude of this field times the area of this face. The area of this face is of course a times a, and therefore the total flux through the entire cube equals E naught times a cube. There is only one face of the cube which has any flux through it, so this is that flux, and this total flux will of course be equal to the enclosed charge inside it by epsilon naught, and this simple equation now gives us the magnitude of charge enclosed inside the cube, and it will be equal now to epsilon naught E naught a cube. So the charge enclosed inside the cube has been calculated. Fairly simple, easy calculation here using the field, the direction, and Gauss's theorem. We were able to find the magnitude of charge enclosed in the cube. Later on, we will be looking at the same problem again using a somewhat different approach. What I'm going to do now is I'll give you another version of Gauss's theorem, which you might call perhaps the microscopic version of Gauss theorem, and then later on we'll be employing that microscopic version of Gauss theorem to solve this problem as well. So our next topic of discussion is the microscopic version of Gauss's theorem. Now let's say we have a region of space here in which we'll be determining the microscopic version of Gauss's theorem. Let's say this is our x-axis, this is the y-axis, and this here is the z-axis. In this region of space, there is some electric field which varies with the location. So at every different point we have different magnitudes of the electric field, and what we are really interested in is the relation between the electric field and its variation with the space coordinates, and also the density of charge distribution in this space. So we'll be doing this kind of calculation using what is called our familiar Gauss's theorem. So consider now a small cube over here. I'm considering a tiny little cube, or rather a cuboid actually, over here. All the sides of this cuboid are parallel to the x, y and z axes. Now this side, which is parallel to x-axis, has a length del x. The length parallel to the maybe I've not drawn it properly enough. I need to redraw. Yeah. So this is the little cube we are considering. This here is del x, the length parallel to x-axis. The length parallel to the z-axis or the z-axis is del z or del z, and the length which is parallel to the y-axis, this length here, we'll call it del y. Now, to start with, I'm going to consider two parallel faces of this cuboid. One is this surface here. This surface is parallel to the YZ plane and it's on the left side of the cube. And let's consider this surface here, which is again parallel to the YZ plane, and it's on the right side of the cube. Now in this space here, the electric field is variable. So we have variable electric fields. The electric fields have x, y and z components which are variable. But if you look at these two faces, only the x component of the electric field will be perpendicular to them. The y and the z components of the field will be tangential to these faces, producing zero flux. So on these two faces, only the x component of the electric field produces a flux. Let's say over here, the electric field is Ex. The x component of electric field here on this face is Ex, and on this face it is Ex plus del Ex. Since the electric field varies with x coordinate from here to here, it has undergone this amount of change. Now let's calculate the flux on these two faces. On this right hand side face, this one here, the flux will be Ex plus del Ex times the area here. Now the area here is del z by del y, del z times del y, I'm so sorry. So del z times del y, that's the flux through this face. The flux through the parallel face over here will be minus Ex times the same area del z del y. Now why minus? Because electric field lines are entering here, and plus over here because the field lines are leaving this surface. So the flux d through these two surfaces, if you take Ex times dx del x del y, Ex times del x del y minus Ex del x del z del y, Ex into del z del y minus Ex del z del y, that comes out to be 0. And so you're left with del Ex del z del y. That's the total flux through these two faces. Del Ex, notice the pattern, del Ex times del z del y. Now if you consider the other two pairs of surfaces as well, their fluxes will come out to be del Ey times del x del z plus del Ez times del x del y. This is the total flux d phi through this entire cube. Now this total flux del Ex into del Z del Y plus second term del Ey into del X del Z plus the last one del Ez del X del Y, they all add up to give you the total flux, and that total flux will be dq, the total charge enclosed inside this little cube, divided by epsilon naught. Now, the volume of this cube is del x, del y, del z. The volume of the cube is del x, del y, del z. We divide by the volume on both sides. Remember, the volume is dV del V equal to del x, del y, del z. So we now divide both sides of the equation by this dV, and when we divide these terms by del x, del y, del z, we end up with, now if you divide this by del x, del y, del z, del y cancel out, and we are left with del Ex by del x. Then next, if you divide this by del x, del y, del z, you are left with del Ey by del y, plus divide this by del x, del y, del z, and you have del Ez by del z. And on the right hand side you have 1 by epsilon naught times the charge dq on the cube divided by its volume dV. Now the charge dq in this volume dV, when you divide this dq by dV, you get the volume charge density inside the cube, and therefore you now have del Ex by del x plus del Ey by del y plus del Ez by del z, and it equals the volume charge density rho divided by epsilon naught. So we've got this equation here, which is our microscopic version of the Gauss's theorem. Now this is very interesting, and I'll be applying this microscopic version of Gauss's theorem in solving our previous cube problem, and it kind of makes the solution a little bit easier for that particular question. So let's now take up the previous problem once again. We are revisiting that previous problem where we had a cube. This is x-axis, y-axis, z-axis, and we had this cube here of side or edge length A. The edge length of this cube is A, and the electric field in this entire region of space E is E naught x I cap. That's the electric field in this region of space now. And we are interested in calculating the total amount of charge inside this cube. Now it's a fairly simple problem once we know the microscopic version of Gauss's theorem, which says del Ex by del x plus del Ey by del y plus del Ez by del z is equal to volume charge density by epsilon naught. Now in this case the electric field varies only with x and not with y and z. since it does not change, does not vary with y and z, these two quantities here, del y by del y and del z by del z, these derivatives are now 0. Only this is non-zero. Now if you look at this, Ex here, this field is along x direction, so this is Ex. Its magnitude is E naught times x. And therefore del Ex by del x equals E naught. Now substituting this over here, we get E naught equals rho by epsilon naught. And from here we can easily calculate rho, which comes out to be epsilon naught times E naught. So we now have the volume charge density inside this cube, which happens to be constant because there was only one, the power of x here was 1. If it was variable, then the rho also would be variable and would lead to a more interesting solution. But keeping things simple here, this rho equals epsilon naught E naught here, and therefore the total charge inside the cube will be this volume charge density times the volume of the cube, which is a cube. And so you arrive at the answer. The solution is that much simpler using this approach here. So this is this session here, this video was on some simple kind of applications of Gauss's theorem. In the next video, we will be discussing about the concept of electric potential. So the next video on electrostatics will involve the concept of electrostatic potential. Thank you very much for watching this video. Please keep supporting the channel. Please keep your feedback and comments coming so that I get to know how well you're able to receive the content in these videos, and if I need to make things better somewhere, I would definitely love to know it, and also ensure that this gets done in the upcoming videos. Please keep the feedback coming, and like and subscribe to the channel if you enjoyed watching this video. Thank you very much.